Hey guys, it's Han here. If you come to this repository because you search for an implementation of Dr. Kim's BlockFL paper, it's not a surprise. But I have to apologize first, as the BlockFL implementation hosted in this repo is incomplete, and I have deprecated the development. Plus, the code here uses a linear regression model rather than a neural network model, so the repo itself may have very limited research value. I suggest you take a look at my VBFL work, which is hosted in another repo named VBFL on my GitHub. It is a successor project in which I have reused a lot of code in this deprecated repo. But please know that VBFL is a blockchain federated learning simulation that runs on a single machine. That also tells the main coding difficulty as why I have given up the development of this framework. It is that I could not sufficiently make the nodes become fully distributed and autonomous. The code is built upon the Flask framework, which to my best knowledge is designed for web development, but not for web or system automation. So I searched for some solutions, and guys on Stack Overflow recommends me use Tornado or Celery rather than Flask, but I couldn't squeeze time to change that. But you may find it worthwhile to build upon an executable version of my code for your own work by reusing some code in this repo, as I have some node functionalities such as the block class, the blockchain class, ready in Python for this BlockFL implementation. Also, please note that I extensively referred to this IBM tutorial when I was building the blockchain architecture. So you can also go here to study if you just want to write a basic blockchain system in Python. So in this video, I will show you how you can run an executable version of this unfinished project in a sequential manner. So in this way, you would get an idea of what is in the code and which part you wish to reuse. And I hope it could help you in your own work. Okay, so the first step is to clone the repo. I will do this from scratch. And let me see. Let me run this first. I suggest you have a Conda environment that has installed Python 3.7 or any newer version, and Flask 1.1.1, which is the Flask version I used for the code. And then, let me cd into directory first. Please first check out the dev branch, as the latest commit in the master branch will not actually run. So the system requires at least one worker and one miner to operate. And of course, you can create more than one miner or workers as you wish. For simplicity, I will first demonstrate creating one worker and one miner, and then I will show you using the same commands we can create more workers and miners and make them join the network. The running steps are basically just how you run a Flask application, and you can find some of the commands I'm going to use on this README page. Okay, so to run a miner, first execute this command. This is to export a miner to port 5000 on localhost, and you may use a different port as you wish. And then the miner window is ready. Then in a separate window, execute this get command to get the miner to run. You can already see some output saying that miner is waiting for workers to upload their updates now. Press enter to continue. We will get back to that later. To run a worker, the steps are essentially the same. First, we execute this command to, we have to do this in a separate window. To export a worker node to port 5001 or any port you want. Then in another separate window, we have to send this get request to 5001 to get the worker to run. Okay, then you can see there is some dummy data the worker has generated at its initialization, and we will get back to that later as well. Okay, we can actually close these two windows as once they are already running. Now we have one miner and one worker in the network, but they are not aware of each other because they are two separate nodes, assuming we are simulating a public blockchain environment. Therefore, they cannot communicate at this moment. To let them know each other, we have to register one node with the other node. So registering also means that you let one node join the other node's network, as I will show you how you can register the worker on this 5001 with the miner on 5000. Again, in a separate window, you can use these commands. Let me copy all of them. You can use this command to register 5001 with 5000, in which 5001 is the registrant and 5000 is the registrant. If we execute this command successfully, you can see some output from the miner and the worker that they have added each other to their peer list. So they can now communicate. Okay, then I will start demonstrating the system in a sequential mode for BlockFL, which means it is not autonomous for those nodes, but you have to manually give out orders by pressing enter for the nodes to go into the next step, which you will see. So let's have the original BlockFL paper as a reference. Okay. So the first step is local model update from the worker side. So let's go to the workers window. Before I continue, as I mentioned, we are using a linear regression model, and I followed the gradient descent formula from Professor Andrew Ng's Coursera machine learning course. By the way, this is a free and great course, and you may already have heard about it or studied that. The thing is that in order to make this linear regression model converge, every worker should have very close, if not the same, values for the coefficients. This H, which I defined in the code in this server worker. In this server worker on the line 193, this line. Because this linear regression model, I think, it is designed to be trained on a single entity, on a single machine. But this single tweak, as we have defined the same coefficients for every worker and make them to run to join the network to train together, this simple tweak can make it learn in a distributed manner. So let's continue and let this worker do its gradient descent by pressing enter in the workers window. Okay, step 2 is let me get this paper. Step 2 is local model upload. In this step, the worker will randomly pick up a miner from its peer list to associate with. But in this special case, the worker will choose this miner as we have only one miner in the network. In the next communication round, I will add another miner and you will see some differences. Let's continue. After the association, the worker will upload its gradients to the miner. You see, from the miner side, it has received local model updates, which are the gradients. Okay, now worker has nothing to continue, but waiting for the block from its associated miner. Let's first press enter in the miner side. Okay, so the next step is miners have to do cross verification, in which they will first broadcast, as I remember. Yes, they will broadcast the received model updates to each other, verify their own received updates, and cross-verify the updates broadcasted from other miners. Since there is no concrete validation scheme in this paper, I just let them verify the dimension of the uploaded gradients, which should match the dimension of the data, just for the presentation purpose of this code. In VBFL, however, we have designed a novel validation method for the neural network-based federated learning, and I invite you to take a look at here. So in this case, since we have only one miner, it will just do self-verification. So let's continue. Okay, say since it did not broadcast nor received any broadcasted updates, there's no output from the broadcasting step. Later I will add some more miners to demo this functionality. So let's continue to do verification. Okay, you can see the cross verification is called, yes. But in this function, the miner will first do self-verification, then do cross-verification. You can see the miner's initial reward is 0, and after the worker's uploads are verified, which is if the data dimension matches, the miner will reward the worker by the number of data points the worker has provided. And this number is hard-coded as 5 for presentation purpose only. You can also see the worker gets reward from its output. You may need to implement your own concrete rewarding mechanism, however, and we implemented a proof-of-stake inspired mechanism in VBFL paper. So the miner will also receive rewards by performing the verifications, and the reward the reward is the number of the data dimension, which is hard-coded as 3. So after self-verification, and since it hasn't received any broadcasted uploads, it does not get rewards from cross-verification. So the total reward is 3 after self-verification. No broadcasted updates. So next, miner will begin to mine its block, and based on the BlockFL paper, we are using proof of work, and implemented as nonce increments. Nonce increments. So let's continue. You can see that before POW, the nonce is 0, and after POW, the nonce is 315, with the block hash value as this. Oh, by the way, you see the POW difficulty is set to 2, which you can, let me make this bigger, which you can redefine in the code. That's why its hash has 2 leading zeros. And please note, in a multiple miner setup, the miner can receive a propagated block if there is another miner that mines quicker than this miner. In this simulation, whichever miner you allowed to proceed first by pressing enter, the miner will be the winning miner. But ideally, the nodes should run autonomously and compete in POW, and let the POW itself decide which is the winning miner. In my VBFL project, I tracked the mining time for individual miners to decide the winning miner, at which I recommend you take a look. Okay, since we only have one miner here, itself will be the winning miner, and it will, you see, the next step is to propagate the block. Let's first continue to see what happens. Since there is no other miners, so its propagated block will be lost in the wild. And later you will see the propagation of the blocks when I add more miners. Okay, so next it will add its own block to its blockchain, which is a genesis block in this case. Let's continue. So its own block has been added to its blockchain, which is a genesis block. So next step is to request associated workers to download the block, which is the only worker over here. Let's continue. And you see that this worker has received the global update from this miner, which I remember should be the average gradients for this linear regression model. And the worker automatically performs a global model update, even though in this case it's like a single entity. And both of them can now enter the next communication round. Actually, the miner is already in the next communication round. So at this moment, I can demo you another functionality, which is that I have built several endpoints. Yes, several you see endpoints which can be used to request some information about the system. Again, I learned this from the IBM tutorial. So for example, we can query the chain information by this chain API. So if we run it here to get 5,000 chain, you can see the chain information is returned by this miner. And let's query the chain information by this worker as well. Let's see. And the worker's chain is returned. And you can verify that they are in sync by the block hash of the genesis block, right? Block is the same and nonce is the same. Okay, so for a more complete demo, let me add one more miner and two more workers. And by the way, there's code that allows a registrant to sync with the registrar for the registrar's blockchain and the purist or registering. In other words, when node A joins the network by registering with node B, node A will suck node B's blockchain and the purist will suck in its blockchain and purist. Therefore, if we add 3 more nodes here, the new nodes will have the genesis block from these 2 old nodes. So our system allows nodes to join the learning progress in the middle. Okay, so let's add one more miner at port 5002. Let's use this window. And let me make 2 more workers at 5003 and 5004. Okay, but now let's first register them so they can sync their chain before they begin. Like I said, 1 second, let me grab a new window. We don't need this window now, actually. I think it's too narrow. I don't seem to be able to close it. Whatever. But as I said, when you sync with another node, when you register with another node, then the other node will give the new node its chain information and a purist. Okay, so let's register 5002 with 5000. This is okay. In this way, these two miners will know each other, and also you can see that 5002's purist has 5001 as well, though they have never communicated with each other. Okay, so let's register the rest 2 nodes as well. Okay. And by the way, you can look at this wiki page to know what endpoints are available, and you can code your own by searching for at app.route. I can show you in this code. Okay, this app.route, which is a Flask syntax, I believe, in the code to write your own endpoints. let's continue the sequential learning. Let's first, let's first run these 3 nodes. Okay, so we have to get 5002 and 5003 and 5004, and we can close these 3 windows afterwards, or it would be so narrow. Okay, so we can first let the workers continue. This is a worker. That is a worker, right? Yes, this is a worker. Is already in communication round 2. Let's make it continue. Let's make them in the same page. Okay. Oh yes, immediately, you can spot that they start from communication round 2, even though they are new nodes, right? Because they have synced the chain with the with the nodes that already in the network. Okay, so let's do local model update. They have already done that. I'm sorry. Okay, and then let's associate the miner with the miner. Okay, you say this worker is associated with this miner, and this worker is associated with this miner. So the association is quite random actually. Okay, now let's demonstrate the broadcast of local model updates, cross verification, and block propagation between these 2 miners. Right, I have to keep track on that. Okay, let's press enter for each miner. Now let's first let the new miner broadcast to the old miner. Okay, and you can see the old miner receives them, and the old miner also will broadcast to the new miner. Right. Okay, so we can now let them do verification. You can see with broadcasted uploads in output, now a miner gets rewards for both self and cross verification. So let's take a closer look. So before verification, the reward was 3, and after self verification, the reward became 6. So there is a 3. So which means this miner has received 3 has received the uploads from 1 worker, right? Because the data dimension is 3. And then after cross verification, this miner gets 6 more rewards because this miner actually sends the uploads that are from these 2 workers. So the total data will be the dimension will be 3 plus 3 because those are from 2 workers, right? So there will be 6 more. So after cross verification, it became 12. So totally, it added 6. So totally, it became 12. And for this one, because the self verification before that it was 0 because it's just newly joined, right? So after self verification is 6, and after cross verification is 9, because cross verification is from this miner who gets just the upload from 1 worker. So the dimension is 3. 6 plus 3 is 9. All right. So let's continue to let's see. Let's mine the block. Actually, I thought it's propagate the block, but let's do that first. Yeah, the next step is to propagate the block. Let's assume this new miner is quicker. Okay, you can see the old miner receives the propagated block, and then the block is also verified, and is added to this miner's blockchain. So the next step for this old miner is to request these workers to download. Okay, let's continue on this old miner. Yeah, the output just says that a propagated block has been added. So we can jump to request the worker to download. And I remember this worker is the associated worker, so this worker will get this block. Okay, see, this worker gets its block, right? So let this miner also add its own block to its blockchain, and then request its workers, these two workers, to download this block. And see, these two workers have also received the block, the same block from this worker, this miner too. So at this moment, if we check all the chains for these 5 nodes, they should be in sync. So let's do a quick sanity check. Okay, that's 5,000, and let's do 5,001, and let's do 2 and 3, and last one is 4. Okay, as you can see that all of them are in sync by the let's see, by the block number. That's block number 2, right? Or block number 2 and other information, such as, say the block hash are all the same, right? Okay, so let me think. I think at this moment, this concludes my demo. And if you continue by following the running orders that I just showed you, the linear regression model would converge. I have done several experiments to prove them with the help of an automation software for mouse and keyboard, as you can see from these plots. So this is the weight prediction plot. As the run progresses, their predicted values are approaching the initially these dashed lines, initially set weights. And this is the next plot. And those are the differences between the predicted weights and the hard-coded weights. They all gradually approach zero because those are differences. Okay, those are the same, but for 10 devices, right? Yes, but I think the remaining usefulness of my code repo is that you may only find it helpful to reuse some functions for your own work, or extend them on top of this code. By going through this demo and look at my code, side by side, you will get a pretty good understanding of each Python function, I think. So if you have more questions, please open an issue or send me an email. I hope this video helps your research, and I would appreciate it if you would share your insights with me about new research ideas in distributed ledger technology and distributed learning. Okay, thank you very much.